Hi everyone, I am Timothy from Cognito Academy. In this video, we will be learning how to draw free body diagrams. So let's hop into it. A free body diagram of an object shows the relative magnitude and direction of all forces acting on that object in a given situation. Usually to find the resultant force on the object given all the individual forces acting on it. Basically, it shows all the individual forces acting on that object. So how do we draw a free body diagram? The first step is to identify the body we are drawing the free body diagram for. Like for this case, we are drawing the free body diagram for the box and not the ram. Next, the actual drawing begins, where we draw all individual forces acting on only that body. In this case, we only draw individual forces acting on only the box. To make drawing easier, we try to draw all same direction forces first, then opposite direction forces, before drawing forces in other directions. This is to make drawing the magnitude of different forces easier. Lastly, take note of the net force on that body, and adjust the magnitude of the individual forces accordingly. The things to note are, we only draw individual forces and not the resultant force on the free body diagram. And we only draw forces that are acting on that body. We do not include forces acting on other objects in the free body diagram. Like in this example of the free body diagram of the box, we only draw the individual forces acting on the box, and not forces acting on the ram. So let's start drawing. In this scenario, we have a box at rest on the table. We are tasked to draw the free body diagram for the box. So we only draw the individual forces acting on only the box. The box experiences gravitational force, which is its weight, acting downwards from its center of gravity. But the box isn't accelerating down, meaning there is a counter force upwards that is of the same magnitude, which is the normal force from the table acting on the box. Note that they are both of the same length because they are of the same magnitude. They have to cancel each other out entirely because net force on the box is 0, since the box is at rest. Take note that weight and normal force here are not action-reaction forces, since they both act on the same object and cancel each other out. Action-reaction forces strictly act on different objects. For further explanation, do watch our Newton's laws of motion video. There are no horizontal forces in this case since the box is not being pushed. Since the box is at rest, net force on the box is 0, so all forces on the box should cancel out, which holds true. Now, the box is being pushed along the table at constant velocity. In this case, horizontal forces are at play. We have an applied force pointing towards the right. Since the box is moving at constant velocity, by Newton's first law of motion, net force on the box is 0, meaning all forces on the box must cancel out. The force that cancels this rightwards applied force is friction, which points to the left at the same magnitude. Now in the same scenario, how do we draw the free body diagram for the table? This section is pretty complicated, so feel free to skip to the next part if you are just starting out. Otherwise, let's continue. So, following our rule, we draw individual forces acting on only the table. In this case, there are a lot of individual forces acting on the table, so we have to approach this problem systematically. Remember that we always try to draw all same direction forces before the other directions. In this case of the table, all forces have to cancel one another out entirely since net force on the table is 0, as the table is at rest. Let's draw the downwards forces first. We have the table's weight. But is that all? Remember that our box experiences a normal force from the table upwards. So by Newton's third law, an equal and opposite normal force pointing downwards will be acting on the table from the box. Now that all downwards forces have been drawn, let's draw the upwards force. There is only one upwards force here, which is the normal force on the table by the ground. Take note that the magnitude of this normal force is the summation of the weight and downwards normal force by the box. So this upwards normal force will cancel out both downwards forces entirely. Now that we are done with the vertical upward and downwards forces, let's proceed on to the horizontal ones. Remember that our box experiences a frictional force from the table pointing to the left. So by Newton's third law, an equal and opposite frictional force pointing to the right will be acting on the table. But we know that net force on this table is 0, so there must be a force that counteracts this rightwards frictional force on the table. This force is in the opposite direction, which is the frictional force on the table by the ground pointing towards the left. Now, we can all see that all forces on the table cancels out, since the table is at rest. Next, in this scenario, we have a parachutist falling at increasing velocity. Let's draw the free body diagram for this parachutist. The parachutist experiences gravitational force, which is his weight, and since he is falling through air, he experiences air resistance upwards. Take note that the parachutist is falling at increasing velocity, which means the parachutist is accelerating downwards, and by Newton's second law of motion, there is a net force pointing downwards. Hence, the magnitude of air resistance must be less than the magnitude of the weight. After a while, the parachutist reaches constant velocity. Similarly, let's draw the free body diagram for the parachutist. The same two forces, weight and air resistance, acts on the parachutist. But what's different here is that since the parachutist is falling at constant velocity, by Newton's first law of motion, net force acting on the parachutist is 0, meaning air resistance must cancel weight out entirely, and hence air resistance here has the same magnitude as weight. In another scenario, we have a block hanging on a spring at equilibrium. Let's draw the free body diagram for the block. The block experiences gravitational force, which is its weight. Since the block stretches the spring, there is an elastic force pulling the block upwards. Since the block is at rest, net force on the block is 0, meaning elastic force cancels the block's weight out entirely, and they are of the same magnitude. Now, the block is being pulled down. Similarly, let's draw the free body diagram for the block. Weight acts on the block, and there is an applied force downwards on the block by the person pulling. And similarly, since the spring is being stretched, there is an elastic force pulling the block upwards. Since the block is at equilibrium, net force acting on the block is 0, meaning elastic force must cancel all downward forces entirely, meaning the magnitude of the elastic force must be equal to the summation of the weight and the applied force. Here in this scenario, we have a horse pulling a cart at constant velocity, meaning net force is 0. Let's first draw the free body diagram for the cart. We have the cart's weight and normal force from the ground, both of the same magnitude acting on the cart. We have the applied force from the horse pulling the cart acting towards the right. And since the cart is at constant velocity, net force on the cart is 0. Therefore, resistive forces towards the left must cancel out this applied force. We can see that all forces on the cart cancels one another out. Now, let's draw the free body diagram for the horse. We have its weight and normal force from the ground, both of the same magnitude and cancelling each other out. Remember that the cart experiences an applied force of being pulled by the horse. So by Newton's third law, the horse experiences an equal and opposite force, meaning to say that there is an equal applied force acting backwards on the horse. Since this is not an ideal system, there are resistive forces acting backwards on the horse impeding its motion. The horse is driving the entire system forward, hence there is a driving force pushing the horse forward. The magnitude of this driving force is the summation of both backward forces, since the driving force have to cancel these two backward forces entirely for the net force on the horse to be 0. And with that, we have come to the end of our video drawing various free body diagrams. If you liked this video and found it helpful, do drop us a like down below and subscribe to our channel. Also, follow us on our Instagram and our website. Links are provided down below. With that, see you in our next video.